And then if at any point my audio gets glitchy, just let me know. Okay, so today we're going to first just brush up a little on unsaturation number. I know you guys did it in a previous assignment, so now we're just going to formalize that. And then once we're done with that, we're going to go into introduction to retrosynthesis and what that entails and kind of the key points of how to approach a synthesis question. So the first thing is unsaturation number. So what exactly is unsaturation number? So it indicates the total number of pi bonds in rings that your molecule has. And this makes it easier to kind of figure out the molecular structure of a molecule just from the molecular formula. So let me kind of write that down. So degree of unsaturation. Which you'll also hear being called unsaturation number. And we'll just abbreviate that D of U. And then that's going to be equal to number of pi bonds plus number of rings. And so let's look at a couple kind of general examples. So if I gave you a molecule kind of like benzene right here, right? And then we have the degree of unsaturation. For a molecule like benzene, the degree of unsaturation would be 4, right? Because we have 3 pi bonds and then an overall 1 ring. So what about something like acetylene? C triple bonded to another C. The degree of unsaturation in this case would be 2, right? So let me put the 1 ring and then 3 pi bonds. And then for acetylene, we have 0 rings. And then we have kind of 2 additional pi bonds to your normal sigma bond. So then what about something like butane? What's going to be the degree of unsaturation on butane? And so that's going to be 0, right? Because we're going to have 0 rings and 0 pi bonds. Okay. So then if I asked you to find the degree of unsaturation for phthalimide, so let me draw that structure. It looks a little something like that. Can someone tell me what they think the degree of unsaturation is going to be?
7.
Yeah, exactly. Right, because we're going to end up having 2 rings. And then we're going to have 1 double bond, 2 double bonds, 3 double bonds, 4 double bonds, and 5 double bonds. So we have 2 rings and 5 pi bonds. Right. So now, what if you weren't given kind of the structure? What if we just gave you the molecular formula? The question is, can we calculate degree of unsaturation from just the molecular formula in a problem? And the answer is yes. So I'm going to give you 2 equations to do this. And Ganem, I think, presented us with the second equation, but feel free to use whichever one you're more comfortable with. So for the first equation, we're going to have degree of unsaturation, and that's going to be equal to 2 times the number of carbons plus 2 plus nitrogen, or the number of nitrogen atoms, minus X, which is going to represent the number of halides, things like chlorine, fluorine, bromine, etc., minus H, which is going to represent the number of hydrogens, all divided by 2. So if we take our phthalimide example, and the molecular formula is C8H5NO2, right? And we weren't given any kind of structure to go along with that. How could we just calculate the degree of unsaturation to kind of have a better idea of what the molecule is going to look like? And so let's try to apply the formula. So degree of unsaturation is going to be equal to 2 times the number of carbons, which is going to be 8 in this case, plus 2, right? That's in the formula. And then plus the number of nitrogens, which is 1, minus the number of halides, which is 0, minus the number of hydrogens, which is 5. And then divide all of that by 2, and then we're going to end up 19 minus 5 divided by 2, and that's going to be 7. So that is kind of the first equation for calculating degree of unsaturation. And then for the second equation, this one looks a little bit different. So you're going to have degree of unsaturation, and that's going to be equal to 1 plus 1/2 times the sum of the number of atoms times number of bonds formed by the atoms. Number of bonds formed minus 2. Okay, so let's take that apart a little and apply it to the phthalimide example again. So we have C8H5NO2. So this number of atoms, that just means kind of how many atoms, how many specific types of atoms do you have? And then how many bonds does that atom like to form under normal conditions, minus 2. So for something like carbon, right, in our equation, we would put an 8 right here, right? That's how many carbon atoms we have. And then for the number of bonds formed, minus 2, right? We know that carbon normally likes to form 4 bonds, and then we're just going to subtract 2 from that, and then we're going to do that with all of the atoms in the equation, in the molecular formula. So let's kind of do the example. So we're going to have 1 plus 1/2, and then we're going to do the sum for all of the atoms. So for the first one, we're going to do 8, right? That's the number of carbon atoms multiplied by the fact that carbon forms 4 bonds minus 2. So that's the first one, that's carbon. Now we're going to do hydrogens. So we have 5 hydrogen atoms multiplied by the number of bonds hydrogen likes to form, which is 1, and then minus 2. And then we're going to do our nitrogen. So there's 1 nitrogen multiplied by the fact that nitrogen likes to form 3 bonds, minus 2, plus lastly oxygen. There's 2 oxygen atoms times the fact that oxygen likes to form 2 bonds, minus 2. And so when we kind of plug and chug through all of that, we're going to end up with 1 plus 1/2 times 16 minus 5 plus 1 plus 0, which is going to simplify all down to 7. So we're going to get the same exact answer. So I guess the key point of this is you can use either equation, so just try to be comfortable with both, but in the end, as long as you can get to the degree of unsaturation, then you'll be fine. Okay, so now we're going to switch gears a little, and we're going to talk about retrosynthesis. retrosynthesis. And so retrosynthesis is essentially a synthesis is a series of two or more reactions that are designed to get to a final product. And you've been doing kind of like getting tastes of synthesis, but essentially kind of the way that the synthesis types questions are set up is that you're given something like compound A, and let's say we want to get to compound D. And so what you're going to figure out is what series of reactions can I do to get to compound D? So you guys have learned a couple of reactions so far, right? You've learned the acid catalyzed hydration, you've learned hydroboration oxidation, oxymercuration, things like that. And so you're going to have to start kind of figuring out how can you piece the reactions together to get different products. And so you guys haven't really done enough reactions where we can give you like super difficult synthesis questions yet. So we're just going to get a really brief introduction to synthesis. And so kind of the secret to synthesis, or you'll hear kind of like a lot of things about how annoying synthesis problems can be, but essentially there's kind of the overall gist of synthesis is you're first going to want to look for patterns, right? That's what organic chemistry is all about. What patterns can you observe in, say, your compound A, and what patterns, what kind of functional groups can you see in compound B? And so that's kind of the overall look at it. So let's look at kind of what kind of patterns you can look for. So the first one is what types of functional groups are present in the reactant. So when I give A and I say, go through two different types of reactions to get to C, right? You're going to want to look at what kind of functional groups do you have in your reactants, right? Do you have alcohols, right? So things like that, those kinds of functional groups. Do you have alcohols? Do you have alkenes? What types of functional groups do you have? And so from that, right, the next thing you're going to want to look at is what functional groups do you have present in your product? So once again, with our A to B to C example, right, in your products, if you have something like an alcohol, right, we've done a couple different reactions that we know of to add in alcohol groups to compounds, right? So you're gonna have to kind of pull back that information and kind of figure out what kinds of reactions do you know how to do to add in these alcohols. But what if you have things like halides as well, right? We also know how to add in those halides. So that's kind of the second thing that you're going to want to look for. Third, you're going to want to look for what kind of reactions do you know to convert one to the other. So if you're given something like A to B, right? And let's say that in our reactants A, we have just a simple alkene somewhere in the molecule. And then B, we see that we're getting rid of that alkene and we're somehow replacing it and adding in an alcohol. So in regards to 3, right, you're going to think about what kind of reactions do we know that can allow us to convert an alkene into an alcohol. And then the last step, or the second to last actually, that thing that you're going to pattern that you're going to look for is going to be thinking about, are any of the reactants, are any of the reactions that you have that you think about, are they going to produce intermediates to the above product? And kind of an example for that, right, is you did a little bit with the ozonolysis reaction, and you know that if you have A and you just treat it with O3, right, you're only going to get the oxonide. And then there's kind of two different things you can treat that with afterwards. You can either treat it with DMS, or you can treat it with H2O2 and H2O. And we know that if you treat it with DMS, you're going to end up with like a mixture of aldehydes plus ketones. But if you treat it with H2O2 and water, right, you're going to end up with a mixture of ketones, and all of your aldehydes are going to be replaced with carboxylic acids. So things like that are going to be important to kind of recognize and see if you're going to have any intermediate steps that you have to address before you can get to the product. And then lastly, you're going to want to pay attention to regio and stereochemistry in both your reactants and in your product. We're going to take a look at some examples that kind of touch on that idea. But essentially, right, the mechanisms that we've looked at and some of the reactions, they all have some kind of regio or stereochemistry element to that, right? Something like hydroboration oxidation, where you're going to have a syn addition that's going to be anti-Markovnikov. Right, so those are going to be the things that you're going to pay attention to. So regiochemistry, right, you're going to want to look at things like Markovnikov versus anti-Markovnikov. When it's stereochemistry, you're going to want to look at things like anti versus syn addition. Okay, so those are kind of the main patterns that you're going to look for. And so it's important to note that whenever you get stuck in a synthesis question, there's usually going to be more than one way to get to the product. Right? As you go throughout the course, you're going to pick up more and more reactions. So of course, there's going to be more than one way to kind of fit together the puzzle to get from, let's say, A to Z. Okay, so let's look at our first example of retrosynthesis and how we can kind of apply some of the basic ideas that we've learned. So let's say we start with this.
Corel?
Yeah.
Something's wrong with your audio, I think. Like you keep breaking up.
Hold on. Let me try switching to Wi-Fi real quick. Is that any better? Is that any better?
Yeah, it's a little better.
Okay. If you can't hear me at any time, just shout at me. So let's say we start with this alkene. And then we have a CH2 group on that side. And so the question is going to be, how do we start from here? And how do we get to something like this? So carbon, then we have a CH3 group in the back, CH3 group kind of in the front, and then a hydrogen right there, an alcohol right there, and so hydrogen right there, and then a hydrogen right there. So can someone kind of take me through some of the steps, kind of what they're going to be looking for as they figure out what type of reaction to go through to get to that product?
Can you hear me?
Yeah.
Look at like if it's anti-Markovnikov or not.
Mm-hmm. And is this going to be anti-Markovnikov or Markovnikov?
I don't know.
Okay, so, right, in this case, right, where is our alcohol group coming in? What kind of carbon is it attaching to?
The least one, least
Yeah.
substituent one.
Yeah, exactly. So is that going to fit in with Markovnikov or anti-Markovnikov?
Anti.
Yeah, exactly. Okay, so we know that our reaction that we're going to be using has to be an anti-Markovnikov, right? Okay, so what else can we kind of pay attention to in terms of the reactants and the products? Are there any other important patterns that we need to look at in terms of kind of functional groups?
Or like stereochemistry?
Yeah, exactly. So what can you tell me about the stereochemistry?
It's anti-addition.
Yeah. Actually, sorry, this should be syn addition. Okay, much better. Okay, so that's going to be syn addition. Sorry, I wrote it down wrong. Okay, so tell me, what kind of reactions are you already thinking about this could be?
Hydroboration.
Yeah, exactly. So how did you get to hydroboration oxidation being the reaction?
It always adds like syn addition, and it is anti-Markovnikov.
Yeah, and then how did you rule out the fact that it's not going to be oxymercuration, demercuration, or some kind of acid hydration?
Those reactions, I mean, oxymercuration is always Markovnikov.
Yeah, exactly. So this is going to be a hydroboration oxidation reaction mechanism. Right? And then you're going to end up like that. And then you're going to have to treat this with with sodium. Borohydride. Oh, my pen is glitching. Okay. But yeah, you guys kind of get the overall gist of that question. Okay, so let's do a second question. My pen wants to work. Hold on 1 second. Okay, can you guys still hear me? Okay, so I will try using my fingers and see how that goes. Okay, so our next example that we're going to look at is something like this, where we're going to have that same alkene, and let's just react it, and we're going to do this reaction, and this time we're going to end up like this. So what kind of patterns are you guys looking for in this case?
Where the OH is being added, like if it's the most or least substituted side.
Yeah. So in this case, where is it being added?
Most substituted, because that central carbon is attached to 3 different groups, so it's the most substituted.
Yeah. And then let me just make a quick adjustment to this question. Okay, there we go. That's much better. Okay, so this is still being added at the most substituted carbon, right? We're going from a carbon that would be secondary right there to a carbon that's tertiary right there, right? So in this case, it's not really following Markovnikov or anti-Markovnikov specifically, but it's still somehow getting to the most substituted carbon. So what other patterns can you kind of see in this?
I have a question.
Yeah.
You said the more substituted one is that central carbon that has like the 3 carbons attached to it, right? But doesn't that already have like an extra hydrogen attached to it? So when you add the OH, isn't that break the octet rule?
It does have an extra hydrogen attached to it. So this is actually going to be an interesting case where you're going to have a hydride shift. So that's why you're kind of getting that alcohol in that position to get to that more substituted carbons. Can you kind of see how if you remove the hydrogen right here, right, and you get rid of that double bond, and you're going to form your carbocation right there. Can you see how if you did a hydride shift, you would end up with your carbocation right there?
Yeah.
Yeah. So that's kind of an interesting thing that you have to keep an eye out for, is whether or not you can have these hydride shifts and methyl shifts in your reaction. Did that answer your question?
Yeah.
Okay. So what do you guys think could be the possible reaction in this case? Anyone? So what are reactions that we know of that can add alcohols?
I'm thinking it would be an acid catalyzed hydration.
And how did you get to that option?
That I got to that option because in acid catalyzed hydration, we know that it's Markovnikov and that the OH is added to the most substituted side.
Yeah, exactly. So yeah, this is going to be the acid catalyzed hydration with H2SO4 and then something like water to get to that product. So does anyone have any questions on kind of how we did that, how we kind of figured out what that reaction is going to be to get to this product?
Could it also be oxymercuration?
So if we think about oxymercuration reduction, right, or oxymercuration demercuration, we know that oxymercuration demercuration is going to add to the most substituted carbon. But now, let me ask you, does oxymercuration demercuration, does it do any kind of carbocation rearrangements to get shifts?
No.
Yeah, exactly. So if we did an oxymercuration demercuration, the OH would always end up at that position instead. There wouldn't be any shifts any hydride shifts that would be possible to cause the OH to be added to the tertiary carbocation. Does that make sense why it can't be oxymercuration?
Yeah.
Okay. So if there's no more questions on that, let's do Example 3. Okay. Okay, so with example 3, okay, with this one, we're going to do a slightly harder problem. And let's say we're given a cyclopentane like this. I hope you guys can still read my weird finger drawing. The hydrogen there, and then we have another methyl right there. And so the question is, how do we get to this product here? And this is going to be 2, 4, 5, 6. Okay. Can you guys kind of understand what I drew? Okay. So can someone walk me through what their thought process is going to be in this kind of problem? So what kind of functional groups are you noticing in the products? And what kind of functional groups are you noticing in the reactants? And what are some reactions that you know that can get you from the functional group in the reactant to the functional groups in the products?
I noticed the carboxyl acid in the product.
Mm-hmm.
And I
Yeah.
know that I think it's ozonolysis usually produces those.
Mm-hmm. Yeah, exactly. And then ozonolysis, and then what type of reaction? So we know that the first part of ozonolysis is going to be O3. Right? How many parts are there to ozonolysis?
2. So the other one would be the H2O2 and H2O.
Yeah, exactly. So you have H2O2 and H2O. Does everyone kind of see how we got that as being what the reaction conditions are, or what type of reaction this would need to be to get us to that product? Okay.
I have a question.
Yeah.
So I know like the product is like the unraveled form of trying to do like the ozonolysis, but I was curious as to why like if you were to put numbers on the structure like for like the longest chain, like why would there be a double bond for O on, like, let's just say if I was numbering from left to right, like why would it be on like, well, why are the double bonds there and not like the ends kind of?
Yeah.
Like not the double bonds would kind of have to be like if you were to make the pentene, like the cyclopentane, they would have to be kind of at the end, the O's or something. So that when they circle around, they're kind of like next to each other.
Mm-hmm. Yeah, so the easiest way to kind of look at that and in terms of where the double bonds are going to be, can you hear me still? Or am I? Okay, is to kind of just from the starting material to label out the number of carbons that we have. So if we have 1, 2, 3, 4, 5, right? Then when you're drawing out your products, right, you're going to want to first draw in carbon 1, right? And we know that's going to be that carbon. And then if we look at carbon 1, we see that it's going to be where our double bond is. Am I cutting in and out, or can you still hear me clearly?
Oh, I could still hear you. Yeah.
Okay. So we know that carbon 1, right? It's going to be attached to our double bond. So that means that carbon 1, it's going to need to have a double bond to oxygen after the ozonolysis, right? We see that carbon 1 is also attached to a hydrogen. And so if we're doing hydrogen peroxide with water after ozonolysis, that hydrogen is going to need to be replaced with an alcohol. So that makes sense. And then the last part of carbon 1 is it's going to attach to carbon 2. Right? So let's draw carbon 2, which is going to be here. So now we move on to carbon 2, and we see that carbon 2 is going to be attached to a methyl group, which is that one right there. And then it's going to also be attached to like the rest of the molecule. It's going to be attached to carbon 3. So this is going to be carbon 3, right? And carbon 3, it has no other kind of substituents. It's just attaching directly to carbon 4 with 2 hydrogens that we aren't really going to focus on. And so that's carbon 4, right? And then once again, carbon 4 isn't attached to anything specifically. It's just attached to carbon 5, right? And then that's going to be carbon 5. And then when we get to carbon 5, what we'll notice is that that's the second part of the double bond. So that means that one of the attachments to carbon 5 is going to have to be the double bond to oxygen, right? And then another attachment to carbon 5 is going to be that methyl group, which is going to be here. Right? So do you see kind of how we can take it apart to put it back together?
Yeah, I had counted it wrong. That's why. So I was like, oh, that makes more sense. Since you started from like the right, yeah, because the OH yeah would replace the H.
Mm-hmm.
Yeah, okay, thanks.
Yeah, okay. So then our last example for today is going to be this one. And so what if we start with something like this? And then we have our hydrogen and our methyl group right there. And then what type of reaction can we get to that would get us all 4 possible stereoisomers? And then we're also going to get this product where we get that hydrogen, bromine, and then on the other carbon, CH3 and H. And then we're also going to get the enantiomers of each of these. So what does that tell you about what kind of reaction this could possibly be? Do you think that the reaction is going to be very stereoselective? What about the regiochemistry? Is it going to be anti-Markovnikov, Markovnikov?
I was thinking it was a radical halogenation.
Why do you think it's radical halogenation?
Well, okay, so the BR is in the least substituted carbon, and but then again, like it's syn addition, it's not anti addition. So well, yeah, I just knew it was like anti-Markovnikov, so I knew it had to be like either that hydroboration, but yeah, I guess those are the only 2 things I'd point out. Just that there's syn addition and it's anti.
Okay. Does anyone want to add to that? Does anyone else agree that it's going to be the radical halogenation with HBr? So what kind of reactions do we know that can add in bromines?
hydrohalogenation?
Hydrohalogen.
I don't know if radical halogenation is the same as halogenation.
So with, do you mean the one with like something like HBr and radical, or do you mean something like HBr and water?
HBr and water.
Okay.
Yeah.
So if we think about HBr and water, what kind of addition is that going to have? What are going to be some of the functional groups that you would find in the product?
Is it like an alcohol, OH,
Mm-hmm.
and the BR,
I
like
should have
the
said,
halogen?
yeah.
Yeah.
Right. You did HBr and excess water. So is that going to add in a bromine to our products?
Yes.
So with HBr and excess water? So this would be the halohydrin formation reaction.
So no.
Yeah, no. Do you know why, right? Can you see why it's not going to add in bromine if you do HBr with excess water?
I don't see it, but I will like look at my notes later.
Yeah, so, right, with this, when you take off the H from your HBr, you're going to be left with OH, and that's going to attack the carbon that's going to attack the carbon a lot faster than the negatively charged Br. So you're not going to end up adding a Br to your compound, right?
Yeah.
So what other reactions can we think of that are going to add in BRs?
The hydrogen halide addition.
Hydrogen halide addition, so something like just HBr, right? With just normal water, like that.
I have a question. So I thought there's one with like a hydrogen halide with peroxide.
Yeah, there is. So something like HBr with ROOR.
Yeah, that's what I meant.
Oh, this one? Okay. So why do you think it's that one? I think Nestor touched on this earlier.
Because there's no OH, so there's no, it's definitely not the water one because there's no OH attached to it. And so then it has to be that one because the hydrogen and the bromine both goes on it. I don't understand how like to explain that other than that.
Yeah, no, that's exactly it, right? So with this mechanism, if we look at what kind of substitution, where is that bromine, where is it being added? Is it most substituted, least substituted?
Least.
Least, yeah, exactly. So if it's being added to the least substituted, what kind of addition does the radical addition of the halide using peroxide, what kind of addition does it do?
Then,
Syn?
yeah.
It should be, holy crap. It should be anti-addition.
Yeah, okay, you're both right. It can do both.
Oh, both?
It can
Oh,
do
that
both
makes
syn
sense.
and,
That's
yeah.
why I'm confused. Okay.
Right, because you're going to end up with a radical, which is kind of like a carbocation, and you can attack from either the top or the bottom. So we know that HBr can do both, which would make sense for why we have two possible structures and enantiomers. So now, do we know that HBr and hydrogen peroxide, is it going to do an anti-Markovnikov or a Markovnikov?
Anti-Markovnikov.
Yeah, exactly. So you all agree that this is going to be the right answer for how to get to that product? Yes, no, maybe so.
Yes.
Okay, yeah, you guys are completely right. So this would be an HBr addition using a radical mechanism. Are there any questions on that? Okay. So if there are no more questions on that, that is the end of what I had for you today. You guys can ask questions on anything you've done within the past, I don't know, how many weeks? 2 weeks, 3 weeks? Yeah.
I have a question about the 2 examples before when you said it was I forgot what it was called. The acid catalyzed hydration.
Mhm.
I think, wait, what example? It was example number 2, I think.
Yeah.
Yeah, that one. My question is, why can't it be like just water or H3O plus water?
So that's the exact same thing as this, actually.
Okay.
Right? So H2SO4, you can think of it as H3O plus, just a strong acid, and then this is going to be the water part of it. So it's the same exact thing, acid catalyzed hydration.
It doesn't matter what acid you have, it's just an acid.
It's just a strong acid.
Okay, thank you.
Yeah. Mm-hmm.
Wait, what's another name for the acid catalyzed hydration? Is there another name for it or no?
I don't think there's another name for it. Nothing that I can think of. No, nothing.
Okay.
Do you mind showing your slide in the beginning that had like equation 1, I think, for unsaturation?
Yeah. There we go. Equation 1.
Yeah. Okay, I'm good.
Okay. What other questions are there?
I have a question about like the patterns that we see in retrosynthesis. So the first and second ones were functional groups on reactants and products.
Yeah.
So far we know that could OH be considered a functional group that we look for? Okay. And
right? That's the alcohols, right?
Mm-hmm. Is that the only functional group we know of yet?
You also did some stuff with halides, right? With like adding Br, using Br2 and like Cl2 to add in 2 halides, using just like a radical mechanism with HBr to add in a bromine. So those are kind of the 2 main functional groups I think you've gone over. I don't think of anything else. But yeah.
Okay. Got it. Will we ever get like, do we always have the final product when solving these, or do we ever get like anything in the middle of a mechanism and we have to identify that reaction?
So usually the way that you'll get these kinds of questions is that they'll usually give you kind of what you're going to start with and what you're going to end with. And as you get more and more mechanisms, I think the most kind of synthesis, the longest synthesis question I had to do in 3570 was like 5 steps, where you had to get from part A to part B to part C to part D, then to part E. and then you had to like know what all of the reactions would be in between that to get to part E. With like the amount of reactions we've shown you, we can't really do kind of a longer type synthesis, but eventually you'll get to that point as you get more and more types of reactions that can create more and more functional groups.
Okay, thank you.
Mhm.
For the first unsaturation, the first degree of unsaturation,
Mhm.
for that first equation, could you identify the variables again, please?
Yeah, of course. Okay, so 2C, that's just going to be 2 times the number of carbons, right? And then N, that's just going to be number of nitrogen atoms. X is going to be number of halides. And then H is going to be the number of hydrogen atoms that you're going to have.
Okay, thank you.
Mm-hmm. Can you still hear me? Okay, I think that's better. What other questions do you guys have?
I think like on Wednesday's lecture, we went over this equation thing. It was like HBH4, no, HBH2 or BH3 with like a CH2 double bonded to a carbon with an R group. I don't know if that makes sense.
So let's.
Yeah, I didn't really understand that one. And I don't remember the name. I don't know if it's hydroboration or not. But
Yeah, so that's going to be your hydroboration oxygen. Cool. Okay, BH3, let's just do THF. And then what was the alkene?
I just wrote like R2C double bond CH2. Like, yeah.
Oh, I got it. Yeah.
I don't, yeah.
So this is going to be your hydroboration oxidation, right?
Yeah.
And so when you do this reaction, right, where is the alcohol going to add in? Is this a Markovnikov or an anti-Markovnikov reaction?
Is it anti?
Yeah, exactly. It's anti-Markovnikov. And then is it going to be syn addition or anti-addition?
Syn?
Yeah. So then when you kind of do that product, right, which carbon is going to have the alcohol if we know that this is going to be anti-Markovnikov?
The right carbon?
Yeah, exactly. And then what is the carbon on the left going to have?
That's what I don't know. Is it like A hydrogen or a boron?
It's going to be the hydrogen.
A hydrogen.
So, so the way this reaction works is that you're going to first be attacking your boron. It's going to attack to the carbon that's least substituted. And then when it attacks, it's going to donate one of its hydrogens, one of its 3 hydrogens, to the carbon that's more substituted on the other side of the alkene. And so you can do that 3 times because the boron has 3 hydrogens, right? And then you're going to be replacing the boron with an alcohol 3 times. So that's why the alcohol is just going to end up replacing the boron on the less substituted carbon. Does that make more sense?
Yeah. And the alcohol comes from like water, or is it just OH?
Yeah. So it's going to come. Yeah. Yeah, it's going to come from just like water and hydrogen peroxides in there.
That makes sense. Thank you.
Mm-hmm.